So let me do a screen share. Okay. Um, can everyone see the?
Yes.
Yes.
So the as before, I was talking about the fold mechanism, and so there are a couple of things I want to point out about that. In So one of the things that we have to be aware of is that we don't necessarily want the truth value domain to be wedded to the model domain. We want to be able to transport the truth value domain over to, we want to transport the model domain over to a place where the morphisms for the truth value exist, the truth value domain exist. So then the alternative of the signature, so this is kind of the naive signature in which the truth value domain lives inside the category in which the model lives. But for example, if the truth value domain is linear and the model is living over in a topos, that's not exactly how we would like the story to go, right? Instead, what we'd like to do is to use something like Nick Benton's linear nonlinear situation, and transport over from the topos to some symmetric monoidal category with additional stuff, like where the linear mechanisms live. So then the fold mechanism goes from looking like this to looking like this, right? So we have some S which is going from the topos over to some symmetric monoidal category. And then, so instead of just handing it the initial model structures and then accumulating over the recursive walk of the model, in fact, we want S of the initial model constructors. So we've gone from the topos where the model is living over into some symmetric monoidal category, where we can do our truth value operations, and likewise over here, we take S, and again, the reason is because I don't want the topos to be the only way that we get some notion of truth value. Right, we're trying to make sure that we can accommodate linear logic and probability distributions and multisets and all kinds of other things that are not just true and false. And I've argued for that repeatedly in this venue, so I don't feel the need to report that. So now the question is, what is some of the structure that we need to preserve in order to have this situation work? And essentially what we're going to insist is that there's a naturality condition between the identity and S. Right, so so this is the usual naturality square, and then what we can say is, if you have a linear nonlinear situation, then the adjunction that defines the linear nonlinear situation is an example of such an S, although the S doesn't have to be the adjunction. It could be something else, but the main point is that this naturality condition does not does not eliminate all possible interpretations. In fact, we know that the linear nonlinear situation gives us exactly the adjunction of that gives us exactly these kinds of naturality squares, and so so this is not an onerous requirement. So the one way to think about this is you've got some kind of data type living over in your favorite computational universe, like Scala or Haskell or whatever, Clojure. And then over here, you've got some linear computational universe, say a quantum machine or some other kind of thing. And so what we're doing is we're encoding this data type over into this linear world, right? And it's just got to be the case that sort of if you go around the loop, so you go from Haskell to some linear machine and back, that you get back something that can be mapped to your original data structure. That's really what the naturality square is saying. So that's that's not an especially onerous kind of demand, and we can see that there are, in fact, in the case of the linear nonlinear situation, it's met at least by the adjunction. So that's that's kind of the next step in the unfolding, of how we do the model checking. So let me stop there and check and see if that makes sense to folks.
Can you say more about this conversion from topos to symmetric monoidal category?
Sure. Yeah. I mean, basically over here, you don't have products, right? So you don't have the same kinds of projections necessarily. And so you don't like, you'll have a tensor product, but that doesn't give you the same sorts of projections that this thing has. As an example of how this structure is at once more articulate, but also weaker. And so over here, the computational universe is a lot like Haskell, but over here, it's a lot more like linear algebra, but not the, but we're sort of forgetting about the fact that we have the product of vector spaces, and we're only thinking about the tensor product of vector spaces, at least initially, right? And so so when you encode products over here, you've got to add a bunch of tagging, right? And so that when you go back, right, all the tags are in place, so you can recover the data structure, right? So there'll be a whole bunch of, so if you go around the loop, right, so you go S over and S prime back, or S inverse back, then you've got a whole bunch of extra structure that is in the re-encoded version of the data structure, but you can ferret out the original data structure by kind of groveling through all the extra tagging and getting rid of it. Does that make sense?
I think yes. So we can go in circle, and this is still possible, although we don't have all of the information on the.
No, you'll have all the information. It's just going to be richer, right? The linear universe is richer, right? Like this thing forgets a lot of information, right? Think about sets. Sets give you no order. right? Over here, you know, maybe all you've got is arrays, right? Over here, you've got, you know, fancy data types like sets, which forget order and occurrence. And over here, you've got arrays. And so you know the order and you know the number of times something occurs, right? So, so when you go back, you're really erasing extra information, not getting rid of information that that was pertinent. So over here, you there's a lot of information, like the ability to freely copy doesn't live here. It lives here. So if you copy over here, you're aware of what's being spent in order to make those copies. Over here, you're blithely unaware of all of that energy, all of the resources spent into making that happen. Right. So when you go around the loop, it's like, okay, well, these guys don't these guys don't worry about the utility bills, right? They're so wealthy. We would just drop all the billing information.
Yes, yes. So this means that we cannot go back from E to S and have all of the information because we forgot something, right?
Yeah, yeah. But all I'm saying is that the part that the side that's forgetting is over here, not over here.
Yeah, I see.
Yeah, this is a strictly richer. So if you have a probability distribution, as opposed to just set membership, right? Then you know, when you go back, it's like you've figured out some threshold, like 51%, that's going to tell you in or out, right? Whereas over here, you have all those shades of gray.
So we can something, for example, we can compute something in E, and so we can have something in E, and we can transfer this to S, and on both sides we can do the same computation. But on S we will have much more information what happened.
Correct.
And on E we will have the same result, but we will not have information about it.
Right. We forgot. We have the same result, but we forgot how we got there.
Yes, I see now.
Exactly.
Yeah. Makes sense.
Yeah. So and so, you know, I've been fighting. So essentially, right, all of Christian and Mike's paper from last year lives over here. And I've been fighting tooth and nail to say, no, we have to preserve this stuff, right? That's been the story of the last 30 years of the relationship between linear logic and topos theoretic machinery. Linear logic is capturing all this intentional information, which is essential if you want to do complexity analysis, right? And that was sort of why last year about this time I was making so much noise about the parsimonious lambda calculus, right? The parsimonious lambda calculus allows us, because of its origins in linear logic, to do all of this complexity accounting, right? And that's why I'm fighting tooth and nail. I want all the complexity machinery and I want that to be available to the logics that we generate. Right. I want the complexity machinery to be something that you can hand over to your proof mechanism or your model checker, right? So that you can utilize it for blockchain-like operations, like halting it if it's spent too much complexity. Does that make sense?
So, yes. So this means that we can differentiate not between sorting and shuffling. We can differentiate between different types of sorting.
Correct.
Right.
That's exactly right. Yeah. So over here, we should be able to differentiate between sorting and shuffling. But over here, we're going to say yes, but the bubble sort costs more than the sort that you know, I don't know what. Pick your favorite fast sort.
Yeah.
That's the. Yes, go ahead.
Am I correct in understanding that on the S side, you're thinking of some kind of an automaton which has a description, and on the left-hand side, you're thinking of it as purely as structural relationships that you're interested in?
No.
Or am I?
No.
Okay.
Over here, you have plenty of automata, but the automata don't give you, but the automata are free to avail themselves of copying. They're insensitive to the operation of copying. Whereas over here, the automata are extremely sensitive to when a copy has been made. So it's linear. Does that make sense?
Yeah, for now, but I need to learn these things. That's a long way away. Yeah.
Sure. But computational interpretations of linear logic, your best introduction to linear logic. And all I'm trying to do is to preserve all the wisdom that you know the community that so deeply investigated linear logic, like preserve all of that when we're talking about the generations of various kinds of logic, right? So Topos theoretic machinery can't account for this, and we've seen this over and over and over again, right? So like whether you're talking about Benton's work or you're talking about Abramsky's work or Pat Lincoln's work, all of them have shown that the linear world is strictly richer. And I think, you know, Girard and many other people have intuited that the linear structure is closer, much closer to quantum computing. And like you would have to have your head in the sand not to realize that quantum is where a big chunk of computing is going to go. And so if we can't account for the physical architecture, I mean, essentially all I'm trying to do is to make sure that we are set up to make the most of the physical architecture that's going to be abundant over the next 50 years. That's why I'm fighting tooth and nail to not stay over here, which is all classical, and at least have our foot in the door over here, which is much closer to the quantum setting. All right, any other questions or comments?
I would like to ask about true value. So what did you say about the true value domain, right?
Yeah, the truth value. This is the domain of truth values. So for example, true and false is one domain. Top, bottom, 1 and 0, right? That's the domain of linear logic. Or the unit interval from 0 to 1, that's the domain of probability distributions. So those are all domains where we have some recognizable notion of truth.
And I remember that you were talking about Q categories. Is this related or?
Oh yes, exactly.
That's
precisely the whole idea. So that was a concrete model that we used to go and investigate some of these relationships. So the Q category is a relation together with a quantale and some maps that basically ensure that the relation is really a category. So you have a notion of composition and a notion of identity. That's really what's underlying the requirements, the equations that make a Q category be a Q category. So the less than the order relation, which is implicit, the order relation which is implicit in the quantale ends up giving you a category.
Does this mean that Q category, the true value domain, will always satisfy Q category?
No. A Q category is just one example.
One example. I see.
Right. So so the reason we did all that investigation was to have it's like have really understand one example in depth. Right. So that we can we want, because the whole point was that sets are so powerful psychologically. Like if you are a mathematician who is educated in mathematics over the last 50 years, then your mind is full of set theory propaganda. And you can't help it. I mean, you might believe in only finitary sets, or you might believe only in constructive sets, right? Or maybe you're full on ZFZ, but your mind is completely polluted with sets. It is hard to imagine not living in a topos of some kind. And this was especially true for Christian, right, who is a younger mathematician who'd kind of grown up category theoretic, side of things without a lot of exposure to linear. Like I had the benefit of, kind of my the point at which I was really sort of engaging my career from a theoretical perspective is right when linear logic was having its explosion. And so I was steeped in linear logic for many years, and steeped in Girard's program, right? I mean, it's very clear that his geometry of interaction program is aimed right at the heart of providing a foundation and formalism for quantum forms of computation. This is super clear. And so I had the benefit of not being as so tightly affiliated with topos theoretic thinking. But Mike was kind of halfway between Christian and myself, right? He's a physicist, so he's fully aware of quantum mechanics, but hadn't really thought about it in the way that linear logic organizes things. And so working through the Q category structure enabled us to have concrete calculations to develop intuitions about why this thing is not necessarily topos theoretic.
I see.
Yeah. I mean, ultimately, go ahead.
Now that you mentioned sets, I have one question that I wanted to ask you. Another theorem that they want to, or axiom that they want to add to set theory. I'm searching projective.
Oh yeah. The star versus. Yeah. I followed those articles. I no longer remember the details of them anymore, but yeah, I know what you're talking about. I'm kind of a multiverse sort of person. Like, I'm perfectly happy with lots of different cardinalities and lots of different universes where, you've got stuff in between omega and aleph null, and where and universes where you don't have stuff in between, where the continuum hypothesis holds. All of that. I mean, I think it would be fun to like be able to hop back and forth around all of those different worlds. So I appreciate understanding that certain ways of organizing our thinking about cardinality collapse, right? Like knowing that one axiom implies another is important because it allows us to disambiguate different axioms, but to argue philosophically that one of them is better than another without a lot more evidence seems to me to be foolhardy.
And what is the reason why they want to add this additional axiom?
Because it gives them clarity with respect to the continuum hypothesis.
I see. Can you just quickly say what is the continuum hypothesis?
Yeah. So when Cantor discovered that there was a distinction between the infinity of the natural numbers and the infinity of the reals. What he hypothesized was that 2 to the naturals, right? So all the maps from the naturals to 0 or 1 was the cardinality of the reals. There was nothing in between. And he couldn't prove it. And so a lot of mathematicians kind of broke their pick on this until forcing Paul, oh gosh, I'm blanking on the guy's name. It's a wonderful story. I think he was, I certainly know he hadn't gotten his PhD. I think he might have been an undergraduate when he heard about the continuum hypothesis and had a particular, intuited a particular approach and kind of dropped out of all his classes and worked on this.
There is some kind of static or something going on.
Oh.
Is everybody else hearing it, or is it just me?
No, it's sounding good.
No. Yeah.
I don't hear it.
Interesting.
Sorry, Rao. Yeah. The powers that be are tapping into your Zoom line. Hang on a sec. Oh, it's Paul Cohen. So Paul Cohen developed this thing called forcing, in which he showed that the continuum hypothesis, which is that there's no cardinality between the size of the naturals and the size of the reals, is independent of ZF. So you can't use the axioms of ZF without, or sorry, ZFC even. Yeah, you can't use the axioms of ZFC to get the continuum hypothesis. So that's a little bit of the history.
Cool, thanks.
Yeah, it's interesting, but I mean, to me, I don't know, that one doesn't drive me as much, but I do think the forcing technique is quite important. I mean, as computer scientists, forcing is an important technique.
So sorry, can you give me some examples of what ENS are, just so that I have the right picture in mind when I'm like.
Of what examples do you want?
For ENS, right? You said as.
Oh yeah.
I understand like quantum gates and so on. Yes.
Yeah. Okay. So the most common example would be a linear non-linear situation. So this is some topos, so like if you're a programmer, then the computational universe would be like Haskell or Scala or something like that. And over here, the computational universe is some, star autonomous category, some symmetric monoidal category with some additional gadgets. So linear algebra would be an example of well, in particular, so-called Kota spaces, which are a particular kind of topological vector space. That would be what's over here.
I like what you said. Very simple example: set and array.
Yeah.
Super simple.
Yeah. I mean, it's still on physical hardware today. You can copy a value from one array to another. So it's not quite what we're. But that's kind of gives you a flavor. I was just trying to give you a flavor, right? So over in hardware, arrays are easy, sets are hard, right? And in software, because the hardware has a vestige over here, you can implement sets and then forget about the fact that you've implemented them. But, the reality is no programming system comes with sets as a primitive, right? What's primitive is some kind of ordered collection that came from over here.
Yeah, that's interesting. Yeah, yes. In Haskell, like default implementation for sets requires ordering of the elements.
Yeah, that's correct. That's exactly right. Yeah. So over here, like when we go all the way to linear, so multiset, right? That would be, or not even multi, yeah, list or array, right? That's a natural thing. But notice that the notion of predicate is very how do I say, the notion of predicate, when you have when you don't go all the way to linear, but you have only, say, ordered collections over here, that notion is not it doesn't sit well over here. And the reason is because when you're asking for a power gadget, right, there's no way to order all the parts, all the sublists of a list, right? You only have a partial order. And since you only have a partial order, you have one of two choices. Either you say, we don't offer a notion of power gadget, right? Or you say, I have to have choice. So with the axiom of choice, I can now choose an ordering, right? And so I can build you a power gadget. So those are your two options. Whereas in the case of linear, it's not about ordering, but it's about accounting for resources. Did that help you, Pratyush?
A little bit. It'll take me time, but yeah, I'm following it. Yes.
Okay, cool. All right, that's all I have for today. Thank you so much for your time and attention, and we will I'll see many of you in the dev stand-up.
Thanks, Greg.
Yeah, thank you.
Ciao, ciao.